نلاحظ هنا يا شباب زي ما قلنا in pipes he started this work, okay, and he assumed that that drivers should leave or he said that drivers are going to leave a safe distance, and this safe distance he made it this way, that for each 10 miles the drivers he's going to leave one vehicle length, okay, and he came up with this formula, okay, with this equation, okay. When comparing the results or the equation of pipes with the field data, we can see that he is underestimating time headway, safe time headway than the observed, and also that the safe and of course the safe distance gap at high speeds. He is underestimating the safe distance, and at low speed also he's underestimating the minimum safe distance headway, okay. However, later on Forbes started proposed something different. He said that reaction time needs to be that's the governing factor, and the following car usually try to maintain a distance gap proportional to or function for of the reaction time needed, okay. So he mentioned that the minimum headway will be delta t, which is the reaction time, plus vehicle length divided by the speed of the lead vehicle. When looking at comparing Forbes with the field data, okay, we see that he was able to treat the high speed minimum safe distance headway. However, in the mid-range he was too conservative, okay, but at low speed he was not conservative. As you can see, there is inconsistency, and both Forbes and Pipes models, they suffer from one major issue, which is its linear relationship. However, in reality, the field data, you can see there is non-linearity in the relationship, okay. So the third approach was started by General Motors, and they built their theory on the following: that the response of the following car is function of sensitivity and stimuli. What is the stimuli in this case? Basically the response, either acceleration or deceleration, okay. And the stimuli here was always the delta x dot, the difference in speed between the lead vehicle and the following vehicle. Sensitivity, that's basically the key, okay, in all the five models. That's the key difference in the five models developed by General Motors. So we can see here the first model, it said that the response, which is basically the acceleration of the following vehicle, equals alpha, that's a sensitivity factor, multiplied with the difference between the speed of the lead vehicle and the following vehicle, okay. And from field data, they were able to find that at the reaction time, the minimum reaction time is 1 second, the maximum was 2.2, the sensitivity alpha was started with minimum value 0.17 and to 0.74. The average was somewhere around 0.37, okay. So now the dilemma, which value to use, this one or this one or this one. So they came up with a second model where they stipulated that we have two values, either the minimum or the maximum, which make things also more complicated and resolve the issue, okay, and make it kind of judgmental. In order to eliminate that, they studied the sensitivity value alpha versus the inverse of the spacing between the two following cars. And they found there's a perfect straight line, or nearly perfect straight line, relationship between 1 over d and the sensitivity. The slope of this line was alpha node, okay, and that was the milestone in developing the third model. So the third model came like this: alpha node divided by the spacing between the two vehicles multiplied with the difference in speeds between the lead vehicle and the following vehicle. As you can see now, this model started making sense. However, it was a dilemma for Alpha Node. They did several tests, okay, in General Motors test track, and they came up with delta T reaction time 1.5 average value, and 40.3, that's for Alpha Node. Please take into consideration that these factors, this for foot per second. So if you want to convert it to meter per second, you need to make the appropriate, you need to multiply it with the appropriate conversion factor. In Holland Tunnel, it was 1.4 to for delta T, and 2.68, 26.8 for the sensitivity, and so on. However, you can see that it's between 40 to 30, okay, nearly almost foot per second. However, they came up with the fourth model. The fourth model, they mentioned that the sensitivity will be dependent on the speed of the following car. That means if the distance is close and the speed of the following car is high, then most probably this factor will be add up to a high value. So they added the speed here, but the delta x dot is still the same. As you can see, all the five models, what is changing? The alpha, or the sensitivity factor, is changing. So they made a generalized form of the model, which is basically the fifth model. The fifth model, alpha ln m multiplied with the speed of the following car to the power m, divided by the difference, or the spacing between the two vehicles, to the power l, multiplied with the delta speed, the difference in speed. That will give us the response. And if you substitute for, that's the l here, and this is for the m, and this is 0. If you substitute at this point, that's the first and second models, because the first and second models, we didn't have these two terms. Okay? For the third model, the third model is basically L equal 1, so we have this value, this difference, but this one, the speed is not there. The fourth model, it's 1 and 1. Both terms existing. Okay? In reality, we showed that yesterday that the third model, we were able to, do mathematical, assessment and reach to the, bridging from this microscopic behavior to the macroscopic flow model of Greenberg. So that's going to be it for the car following models. Now we shifted to the speed density, or the flow models. So basically the flow models, as we mentioned, it's started first. We agree that at where there's a traffic jam, this is maximum density. Okay, 0 flow at this point. Here, 0 density max speed, which we can say it's VF, free flow speed. Okay, but here at maximum density, zero flow, zero speed. All models agrees on this, and this is something makes sense. V equals 0. However, what goes in between this point and this point has been debatable between researchers and scientists. However, Greenshield was one of the pioneers in 1934. Okay, he assumed a very simple linear relationship between both points. So he said that the speed will start decreasing linearly as the density increases, and he came up with this nice model, okay, where VF, that's the free flow speed. However, Greenberg in the 1959, he came up with this model, which is basically a non-linear model. It's a natural log relationship, okay, and C here is basically V optimum, as we showed yesterday. Then there was Underwood models, 1961. He assumed an exponential function like this one. There are different models. For example, there are some models that assume partially linear, then an exponential function or natural log. So there is until a certain density level. Then after that, this is kind of a combined models. But we are not going to discuss this in this time. Clear? Now for the flow density diagram. Flow is basically the speed multiplied with density. Okay, so here Q equal V multiply K. But if we say, for example, that we have a Greenshield model, which is V equal VF 1 minus K over K jam, then we can say that Q equal VF, okay, multiply K minus K square over K jam. As you can see, this is a parabola. It's a second order, second degree equation. Okay. However, we can get some characteristics from these relationships, as we will see now. Now, some properties for Greenshield model. So that's the speed density relationship. Here is K jam, and here is VF, and here we have the flow density diagram at K jam, and here this is the maximum flow, Q max, and this is K max. If we go up here, that's V max or optimum. I'm sorry. This is K max also, because this point is the same point here, and here that's V max. We want to determine for Greenshield what are these values and what is the maximum flow rate. So we have Q equal VF multiply K minus K square over K jam. If we differentiate dq over dk, what shall we do? What shall we have? We will have 1 minus 2k over K jam equals 0, because if we take the differentiation here, okay, that's the slope of the function should equal 0 at the maximum. Okay, so this will mean that K max, the value of this K, will equal to K jam over 2. As simple as that. Okay, now we want to find VF. Or no, I'm sorry, the speed at Vmax. Vmax equal VF1 minus K max over K jam. So this will be VF1 minus K jam over 2 over K jam. That means this term will go to be half. So Vmax equal VF over 2. That means Q max equal Vmax multiply K max. Substituting with these values, we have VF over 2 multiply K jam over 2. We will have VF K jam over 4. That's the maximum flow rate, okay, according to a green shield model. Clear يا شباب؟ Okay. Now this is the speed and capacity or speed flow rate function, which is basically the relationship between the speed and Q divided by K. And now we started with the shockwave analysis. The shockwave analysis, as we mentioned, is basically it's a boundary, okay, between two states of flow. That's basically the definition of shockwave. Okay, and it's this boundary might be going forward or going backward. Okay, if it's going forward, then it's forward either recovery. That means cars are, were slowing down and now they are accelerating their speeds, and the wave is progressing, or rear stationary, okay, or forward forming. There's the backward, that's the most common that you can see, especially at traffic signals. When the signal turn red, and when the light turns red, Q start building up. Okay, this is a backward forming because it's forming a Q. When the signal turns green, okay, start moving. So that's what we call backward recovery here. This is vehicles were stopped and they starting recovery from being stopped. Okay, here backward forming, vehicles start stopping and forming a queue. Any questions so far? Okay, we're gonna stop here and